Got the hard hat on because we are going to work. Single slit diffraction, an amazingly interesting topic in the IB Topic 11 wave phenomenon. So get ready for some diffraction. We notice diffraction from sound waves all the time because sound waves will come out of someone's mouth and they will then spread everywhere, even if there's no walls to echo off of. With light, it's not quite so easy because, if you maybe cut a hole in a piece of paper and put that over a light bulb, the hole that the light makes when it goes through the paper is going to be about the same size as what the hole is. We don't normally see light spreading out like sound waves do, but that is because visible light has much smaller wavelengths than sound waves. We're talking hundreds of nanometers here. And so when the wavelength is smaller than the opening that it's going through, then you're not going to see this. However, it is noticeable, though, when the wavelength of light is similar in magnitude to the diameter of the opening. Let's say you've got a really, really tiny slit approaching that of hundreds of nanometers. Then you're going to start seeing some crazy diffraction stuff. And I do mean crazy. And that is going to happen when lambda is going to be greater than or equal to b, which is going to be the diameter of our opening or the width of our slit. If the wavelengths are much, much smaller than b, then you won't see anything. Now, to see this diffraction pattern, you're going to need some monochromatic, coherent light from a laser. It's quite easy to make that happen if you have one on hand. And then you're going to need your slit to be of a comparable size or smaller than the wavelength of what you are trying to make diffract. And then you get the pattern that you see here. You'll see fringes with bright spots and dark spots. And you can think that you've got laser light coming in here. You're going to have a dark spot, light spot here, dark spot here, and you'll get these angles of diffraction pattern. Now, here they show that these will be of varying intensity, with the middle fringe being the brightest, and then they get progressively dimmer, etc. Now, the angle theta that you have of these bright and dark fringes is going to be about equal to wavelength over the slit width. B is your slit width. And you could also say that's equal to n lambda over b, where n is an integer of 1, 2, 3, 4, etc. Where the first dark fringe is n of 1. The second dark fringe is n of 2, etc., etc. Now, we'll talk about why this is in the next slide. Oh man, I hate derivations. But here we go. IB wants you to be able to derive the fact that the angle of the minimum spots from single slit diffraction, those dark fringes, will be at an angle of theta in radians, mind you, of lambda over b, where lambda is the wavelength, b is the slit width. So what you want to do is imagine as your laser light, which is monochromatic and coherent, is coming through, each little part is going to act as a separate ray. We call that Hutchins principle. And here, Mr. Dickinson has labeled them all I, Roman numerals 1 through 13. They are going to go far away at a certain angle theta to a screen where they will combine and they'll do some interference type stuff. And they're going to make a dark fringe. Now, we're going to assume a few things. That all these rays, 1, 2, 3, 4, 5, etc., they're all going to hit the same spot on the screen. And we are going to also assume that the ones down here, because it's at an angle, are going to go farther than the ones up here. Now, for example, we're looking specifically at ray number 7 here and ray number 1. We're at a certain angle, and we're saying that this distance here, if this is a straight line, ray 13 is going to be going lambda, one wavelength farther than this one up here, because it has this extra space that it has to go to get up there. Now, you can also say that ray 7, if this is lambda, ray 7, which is right in the middle, this distance here is going to be half a wavelength, lambda over 2. And that's how much farther 7 has to go. Now, hopefully you remember from the last time, if something's going an extra half wavelength, whoa, it's out of phase. Bad things are going to happen because they are going to come together, and if you're out of phase by half a wavelength, destructive interference from those two rays alone, only. Now, let's look at two other rays. Let me drag this on here. Let's look at ray 8 and ray 2. We're going to have the same thing going on. This one has to go a little bit farther, but ray 8 has to go significantly farther, and they're out of phase again with a path difference of lambda over 2. And so these two waves will completely destroy each other with destructive interference. And that will also happen for ray 3 and ray 9, ray 4 and ray 10, etc., etc. So all these different rays are destroying each other to make a dark spot. And just to finish this up, this happens for all of those rays, making that dark fringe at our wavelength, or sorry, at an angle of what we're calling theta, when we end up with a wavelength path difference down here. Now let's look at the geometry of this complete destructive interference. If we consider this to be a right triangle, and we are, then this leg is going to be a width b. This is going to be distance of lambda, and if this is our angle theta, this also is theta. So if we want to use some SOHCAHTOA, this is going to be my opposite and my hypotenuse. So the sine of theta is going to be the opposite lambda over the hypotenuse b. Now, by small angle appreciation, which I appreciate small angles all the time, we can say that sine of theta is the same thing as tangent of theta, and the same thing as just theta, if we're dealing in radians, which we are, and if we're dealing with small angles, which we are. So then we can also say that theta is equal to lambda over b. Now this also happens if this distance were 2 lambda, and we'd end up with a bigger right triangle that would be something like this, where this angle is 2 theta. And this is still b, but this would be maybe 2 lambda, or it'd be a new angle. And so that allows us to end up within something like 2 lambda over b for the second dark fringe. And we could keep going for 3 lambda, 4 lambda, 5 lambda. And that's how we end up getting the equation of theta equal to n lambda over b, where n is an integer like 1, 2, or 3, and this is 4 dark fringes. Now, for solving a problem, you might be asked to find the width of a central bright fringe in terms of slit distance, which we're going to call L, slit width B, and wavelength lambda. Pause this, see what you can do with it. Now you should have realized that the angle to the first dark spot is always going to be lambda over B, and the distance L is from slit to screen, and I'm going to call the whole width from dark fringe to dark fringe W. Now that means this is going to be W over 2 is this distance here. If we do some trig, we can say that the tangent of the theta, which is equivalent to just theta because of small angle approximation, opposite over adjacent, which is going to be W over 2 over L. And we can then say that the angle is going to be lambda over B. So now it's just a matter of solving for W. If I rearrange this whole caboodle here, I'm going to end up with 2 lambda L over B equals the whole width of this fringe. There you go. Try some more problems, see what you can do. I apologize for the boringness of this video.